Hello dear students, welcome back to our mathematics class. In today's lecture, we will learn about the different types or different forms of beta function, in which in this lecture we are going to find with the help of beta function the different form of beta function. So we make the topic as other transformation. Other transformation. Beta function. Beta function can be transformed into many other forms such as beta of mn. You know that the relation gamma of n upon gamma of m plus n, correct? And it is equals to integration from 0 to 1 x raised to m minus 1 plus x raised to n minus 1 upon 1 plus x raised to m plus n dx. We are going to prove beta of mn in the form of x integral 0 to 1 x raised to m minus 1 plus x raised to n minus 1 upon 1 plus x raised to m plus n dx. Correct? Since we know that beta of mn, write in variable y 0 to infinity y raised to n minus 1 upon 1 plus y m plus n dy. We have already seen this relation beta of mn is equals to integration from 0 to infinity y raised to n minus 1 upon 1 plus y raised to m plus n. Now this equation can be written in the form as integration from 0 to 1 y raised to m minus 1 upon 1 plus y m plus n dy plus 1 to infinity y raised to m minus 1 plus y m plus n dy. Correct? Now since we know in previous classes we have learned about integration from a to b f dx is equals to a c f dx plus c b f dx, where a is less than c is less than b. So we can make two integral as integration from 0 to 1 y raised to n minus 1 upon 1 plus y raised to n plus n dy plus integration from 1 to infinity y raised to n minus 1 plus y m plus n dy. Correct. Now we will try to solve this equation. It is our part A and this is our part B. Since part B is equal to integration from 1 to infinity y raised to m minus 1 plus y n plus n dy. Correct. Put y is equal to 1 upon x. We want dy also. Therefore, differentiation of this will gives us dy is equal to 1 upon x square dx. And when the limits of y are from 1 to infinity, when y is equal to 1, in this equation y is equal to 1, this implies that x is equal to 1. Correct? And when y is equal to infinity, then this equation can take place as x is equal to 1 upon y. And if we put y is equal to infinity, we will get x is equal to 0. So, limit of y is 1 to infinity and respectively x running from 1 to 0. Correct? Whenever we take y is equal to 1, we will get x is equal to 1, and whenever we take y is equal to infinity, we will get x is equal to 0. So, limit of x running from 1 to 0 respectively of the value of y 1 to infinity. So, our limit of x is running from 1 to 0. Correct? 1 to 0 and y is equal to 1 upon x. This implies that 1 upon x raised to as it is n minus 1. N minus 1. Similarly 1 plus y. Y means 1 upon x raised to m plus n as it is. Sorry. M plus n, and value of dy is equal to minus of 1 upon x square dx. Correct? Now we have substitute the value of y as 1 upon x and the value of dy and 1 plus y in this step. Now, since we know that integration from a to b f dx is always equals to minus integration of f of x dx, where limits running in reverse order b to a. Correct? Whenever we convert lower limit as upper limit, we have to set minus sign with this integral to get equal integral value. So, by using this property of integration, we can write as minus integration of 0 to 1, 1 upon x raised to m minus 1 upon 1 plus 1 upon x m plus n minus 1 upon x square dx. And this minus will cancel. Minus minus become plus. We will get integration from 0 to 1. Now I am going to write 1 as it is, 1 upon x raised to m minus 1. And here we can write x plus 1 upon x, x plus 1 upon x raised to n plus n into 1 upon x square dx. Correct? Now, we simplify this equation, we will get 1 upon or this x shift to numerator, we will get x raised to m plus n upon x raised to n minus 1, then x plus 1 raised to n plus n 1 upon x square dx. Now shift this denominator to numerator, we will get integration from 0 to 1 x raised to n plus n minus n plus 1 upon 1 plus x raised to n plus n 1 upon x square dx. Since addition is abelian or commutative, that's why we can write x plus 1 is equals to 1 plus x. There is no matter. There is no harm in writing such equation. Now is equals to, we get plus and minus and get cancel. We will get integration from 0 to 1 x raised to n plus 1 upon 1 plus x raised to n plus n, and this 1 upon x square become x raised to minus 2 dx, and we will get integration from 0 to 1 x raised to n plus 1 minus 2 and 1 plus x raised to n plus n dx, which will give us integration from 0 to 1 x raised to n minus 1 and 1 plus x raised to m plus n dx. Correct? And we have the value of b is. Now, this equation 1 will give us, since by equation 1 a plus b is equals to, the a is 0 to 1, y raised to m minus 1 and y plus 1 plus y raised to m plus n dy is equals to plus the part b becomes integration from 0 to 1 x raised to n minus 1 1 plus x m plus n dx. Now replace y by x, we will get integration from 0 to 1 x raised to m minus 1 1 plus x m plus n dx plus integration from 0 to 1 x raised to n minus 1 1 plus x m plus n dx, and we can write in a single integrand 0 to 1 x raised to n minus 1 plus x raised to n minus 1 dx upon 1 plus x m plus n, and it is the another form of or another transformation of beta function in this equation. We have beta function, beta element as integration from 0 to infinity y raised to m minus 1 upon 1 plus y raised to m plus n dy. We have to prove, or we are going to prove integration from 0 to 1 x raised to m minus 1 plus x raised to n minus 1 upon 1 plus x expression with beta mn, and we already know the value of beta mn function in integral form is integration from 0 to infinity y raised to m minus 1 upon 1 plus y m plus n dy. Correct? Now we break this integral into two intervals 0 to 1 and 1 to infinity, and same expression as it is in both integral, because we are breaking only the interval of integration. We are not teasing the expression of the integral, and we have the property of integration from a to b f dx is equals to integration from a to c f dx plus c to b f dx, where a is less than c less than b. So we broke this integral into two parts, and we consider part b as our new expression to solve, which is written as integration from 1 to infinity y raised to m minus 1 upon 1 plus y raised to m plus n dy. Now by putting y is equal to 1 upon x, dy becomes minus 1 upon x square dx, and from this equation we can find x is equal to 1 upon y also. When y is equal to 1, then putting y is equal to 1, 1 upon 1 becomes 1, so x becomes 1. And when y is equal to infinity, putting 1 upon infinity, we will get 0. Finite number upon infinity, we will get 0, x is equal to 0. For variable y, integral running from 1 to 0, and replacing y as 1 upon x, we will get 1 upon x raised to m minus 1 upon 1 plus 1 upon x raised to m plus n, and value of dy is equal to minus 1 upon x square dx. Correct? Now we have integration from 1 a to b f dx is equal to minus integration from b to a f dx. We are changing the limits of integral, or interchanging the limits of integral lower and upper, so we get with minus sign. So to change the integral limits of this integral, or interchange the limits of this integral, we will get minus integration from 0 to 1, 1 upon x raised to m minus 1 upon 1 plus 1 upon x m plus n minus 1 upon x square dx. This minus and minus will cancel. We will get integration from 0 to 1, 1 upon x raised to m minus 1, and after solving this, we will get x plus 1 upon x raised to m plus n, and after solving all these things by using our rule of indices, we can easily get this expression. And since we have equation 1 in two parts a and b, a is already in sequence which we want to find for expression b. That's why we have converted the expression b in the form of integration 0 to 1, and we have these both expression. Now integration is same and the limit of integration are also same, so we can write in a single integral, and we get x raised to m minus 1 plus x raised to n minus 1 upon 1 plus x raised to m minus n m plus n dx. Now it is the another transformation of beta function. We already knew this expression. Now this is new expression for us. So today it is enough for today. Now we will continue in next lecture, and we will solve or see some another transformation of beta function. So keep watching our video and keep in touch with us. Till then, thank you. Bye.